All right, guys, we'll go ahead and get started here. Thank you so much, everyone, for joining us. Today, we have Ingrid Lundeen with the University of Texas at Austin. She's a paleontologist and PhD candidate, and her research broadly explores how animals interact with and are impacted by their environment. This is part of our Human and Wildlife Interaction Speaker Series, which has been going on really since the beginning of summer in June. And we've kind of explored the history of conservation in Park County, and then we've moved to ungulates as well as examples of how humans interact with predators and other animals throughout the world, really. And the idea being that this gives us perspective when we're, looking at human and wildlife interactions in our own backyard, but it also kind of gives us some new ways to look at these things. So without further ado, I'll hand it over to Ingrid and we can go ahead and get started.
All right. Thank you, Amy. All right, I'm going to do my screen share thing. Just a second. All right, thank you so much, Amy, for that introduction. When you first approached me about doing this talk and contextualized it as giving it earlier on in the summer so that I could give an overview of what was going on in the Bighorn Basin before humans got there, that's a great idea. And if I'd known I was going to be giving it from my house in Texas, I probably would have taken you up on that offer. But in either case, I'm happy to be talking to you guys today about the paleontology of the Bighorn Basin, and particularly the Absaroka range, where I've been working for a few years. And please let me know if you have any problems with my speaking or, oh God, sorry. Oh, here. Okay. So my research really broadly focuses, as Amy said, on kind of how animals are adapting to different environments, and in particular, kind of thinking about whether, if there's a difference between where animals can live and where they do live, and typically things might be kind of tropically adapted, so living in these really hot, wet climates where there's really high biodiversity of plants, there's really high relative abundance of resources, so you'll get kind of a you'll get certain animals living in those environments, and they'll seem really highly specialized for that environment. And so what I kind of think about is all the different environments that animals actually do live in. So if you're desert adapted, are you adapted to that dry, hot environment because that's the ideal environment for you, or are you just able to live there? So really thinking about kind of the environments that animals are actually able to live in, and whether they're adapted to these optimal conditions, or whether they're really able to cope in a variety of environments, and what's kind of driving their presence on the landscape in general. So perhaps you're wondering at this point how this fits into fossils, and how, or how fossils fit into the story. And fossils are a really amazing way of kind of considering how animals have responded to climate variation over time. We can use the fossil record as essentially an experiment, a natural experiment in thinking about how animals have been either allowed to speciate or gone extinct in response to a lot of these conditions. And I'm sure if you guys have been attending this human-animal interaction series, you're very aware of kind of the presence of humans on the landscape and how we're impacting our environment. But there's a lot of things that are kind of going into that. And one thing that I think about a lot, and I wish I was in Meeteetse right now to be giving this talk myself, because I love the Bighorn Basin. It has truly, one of the most amazing fossil records in the world. You could definitely argue that, certainly for the time period that it represents. And a lot of the reasoning behind this actually is kind of a historical journey to take. And so I'm going to talk to you a little bit about kind of this historical background of paleontology in Wyoming and in the Bighorn Basin in particular. And then I'm going to talk about some really amazing studies that have been done in recent years. and get a little bit into my own research that is ongoing in the area. So yes, bear with me. All right, so a little historical context to all of this. So Wyoming Territory is incorporated in 1868, right? And immediately following this, we have this massive boom of expeditions going out west to try to scope out the landscape, figure out the best ways to get trains through, get them to the Pacific. And so we've got Ferdinand Vanderveer Hayden here, who was appointed as the head of the United States Geological and Geographical Survey for the territories. And so in 1971, he led this very important expedition. He led a bunch of expeditions, but this one, you could argue it's the most important of all of them, certainly for this story that I'm telling right now, but it was really, really instrumental in establishing Yellowstone National Park, because he went out into northwestern Wyoming and he mapped out the Bighorn Basin and he mapped out Yellowstone National Park, and he thought a lot about what he was seeing there. And you know, it was his survey, in addition to a lot of these really persuasive and beautiful pieces of art that people like Thomas Moran and William Henry Jackson were producing when they were going through Yellowstone with him, that were really important and kind of critical in persuading Congress to establish Yellowstone as our first national park. And so these are kind of these important historical figures, and Thomas Moran and William Henry Jackson were part of this original group that went out there and were seeing the landscape for the first time. And, you know, Hayden himself was really into fossils and rocks. And so he was going through the Bighorn Basin and he was picking up rocks and he was picking up fossils, and he was sending them back to the Smithsonian Institute in Washington, D.C. And in particular, he was sending them to this guy, Joseph Leidy, who's shown in this picture, the kind of sepia tone picture. So Joseph Leidy was an anatomist who became really, really well known for doing fossil descriptions later on. And he was the very grateful recipient of many of the fossils that Hayden was recovering on these earlier expeditions. And this kind of functionally started a series of expeditions west by geologists, anatomists, paleontologists, all interested in paleontology in the Western interior, particularly looking at Wyoming because of these amazing badland exposures where you have a ton of fossils just laying out on the surface. And so one of the really important guys, especially in the Bighorn Basin scene, was this man, Jacob Wortman, who worked quite a bit in the Bighorn Basin and was collecting fossils right around this same time. So in 1880, Jacob Wortman mailed a selection of specimens that he had found in the Bighorn Basin back east to a man named Edward Drinker Cope. And he mailed back about 45 specimens, and of those, 24 of them were new species. So over half of the things that he mailed back were new species. And so Edward Drinker Cope, of course, was like, oh my gosh, this is amazing. We have to go out and collect more fossils. And so he he continues down that path. Now, he had actually been collecting out in Wyoming for a while at this point. And his work out there, in addition to a lot of Hayden's affiliates were really interested in paleontology. And so many of them were kind of collecting fossils and working with them and trying to study them as quickly as possible. And so this is this time period in history that's often referred to as the Bone Wars, or sometimes it's called the Great Dinosaur Rush. But it was essentially kind of a feud between Edward Drinker Cope and this man named Othniel Marsh. And they have kind of interesting backgrounds, the two of them. So Cope, he was this kind of, upper class guy, not really an academic, just very well funded. And then Marsh kind of grew up poor, but ended up getting his uncle, who happened to be George Peabody, who donated a ton of money to a ton of institutions, which is a good guy to have as your uncle. He got his uncle to set up the Peabody Museum at Yale University in New Haven and set him up as the curator and give him kind of funding money and get the ball rolling with his own research. And so Cope and Marsh are both trying to collect things as quickly as possible and describe them as quickly as possible. And the reason for the feud, you could talk for an hour just about that. So if you're interested, I know there are some really amazing documentaries out there, but nevertheless, these guys were openly hostile with each other almost as soon as they knew each other. And this was all made worse by the fact that Cope actually had been involved with the Hayden expeditions pretty early on. And so he'd been traveling around with Hayden. And Hayden told Leidy that he was going to send the fossils back to him. And so Cope was going out there and collecting the fossils that Leidy wanted. And so that kind of caused some tension between Leidy and Cope and Hayden. And anyway, I mean, this whole story is, again, it's a long, the Bone Wars are a whole interesting time period in, the history of science in North America. But nevertheless, we get this essentially a race to name as many species as quickly as possible. And so when you name a new species, you have to name it in a publication. And so essentially, Cope and Leidy are out in Wyoming sending back telegrams saying, oh, I found this, it's new, named, and it doesn't really work that way. So you end up getting a lot of specimens that have multiple names. And to be totally honest, the Bone Wars was an amazing time period because we get so many new species that are suddenly appearing in the scientific literature. But it was also really hard to deal with now in retrospect because there's just a million names for everything. And so it's kind of hard to untangle everything. And we're still kind of dealing with the repercussions of it today. And so I'm giving you all of this background because I want you to just kind of think about the fact that by the time Wyoming was granted statehood in 1890, there was already this ridiculously rich record of fossil collection in Wyoming. And that's basically continued up until today. So, in the early 1900s, the American Museum was setting up these tiny little tents out in the Bighorn, or out in the Bridger Basin. Smithsonian also up into the 70s and 90s, we get collection out there, just really continuous. And this is even from a couple summers ago where I was collecting out there. But so we get this kind of this long-lasting continuous record of fossil collection in the Bighorn Basin. And it should be noted that there are a bunch of basins in Wyoming. And so what is it that makes the Bighorn so special? And, the Bone Wars and fossil collection has gone on all over the Western United States, but why is the Bighorn Basin the place to be when you're interested in fossils? And a lot of that has to do with just the structure of it. So one primary reason that the Bighorn Basin is so amazing, at least in my mind, is that it's surrounded by mountains on all sides. And I'm sure, when you're there, this is so dramatic. And if you're lucky enough to live there year round, I wish I was, you get to see these all the time. And it becomes this kind of fixture on the landscape as something that you don't really think about what it's doing. But one of the things that it's done for millions and millions of years is it's allowed erosion to happen really quickly. And so when we get these mountains with these steep slopes, you'll get more erosion, which allows for greater deposition. So if we've got these mountain ranges on either sides, so this diagram is basically showing what happens when you have mountains and then you'll erode down into these valleys. So sediment will go down into the basins below, and then if that sediment sits there for long enough, it'll turn into rock and then fossilize and preserve whatever is within it. And so we want this kind of environment where we get a lot of deposition. And fortunately, the Bighorn Basin provides exactly that. So this is this just ridiculous expanses, these stretches of rock within the basin that have layers representing slightly different ages. And so when you get these different age rocks all stacked on top of one another, you essentially get this record, this record of what's happening in the environment over time, as long as you're able to use kind of what you know about geology to figure out what came first, essentially. So if you're able to kind of follow these bands in the rock, you can have these really, really long continuous sequences where you can study what's in that one particular band, get a good idea of what that group of organisms looks like, and then apply that to kind of the greater environment. So what this functionally looks like is, people going out there, crawling around on your hands and knees, often wearing gloves and knee pads, trying to find these tiny, tiny fossils. And the ones that I study are mostly, the size of your finger. And they're just teeny tiny, but you're trying to find animals that got trapped in this erosional system and fossilized. or this depositional system and fossilized. And usually when you find something, that's just the beginning. You know, field work is really the fun part, but a lot of times you end up having to go back to home institutions. For me, that's the University of Texas, where I will take fossils that I collect and compare them with known fossils that have species assignments, and then try to identify every individual fossil. So it ends up being this really long process of trying to figure out you know, what you even have in that environment. And if you're lucky, you know, if you're like Cope and Marsh, then maybe you'll have something new. And you can name a new species, and there's a little bit less tension in the scientific community about how you do so now. But if you can kind of construct these community assemblages, then you can get a good idea of how animal communities are changing over time. So we can get kind of this record of you know, how one community of animals slowly evolves into another community. And sometimes you might have extinctions within one community and new speciation within that community that leads to kind of a diversification in a whole separate group of organisms. But all of that is really telling if you're able to tie it to you know, something about the environment, so that you can say these kind of more broad scale you can make these more broad scale claims about why animal communities are responding to certain environmental changes like they are. And so this brings me back to what I do. So coming back to kind of my own research questions, how does this amazing fossil record help us understand animal adaptation in different environments? And if we can link the two, link the fossil record with the environmental change, then we can understand kind of how those, understand the interplay of those things a little bit better. So one of the things that's really critical in all of this is understanding how environments change over time. And so one of the ways that we do this is by looking at global climate change. And so we do this by looking at things called isotopes. And I really debated with myself whether or not I wanted to talk about this, but here we are. So isotopes are basically just different forms of elements with an equal number of protons, but differing numbers of neutrons, which means, you know, in terms of what does this mean in the grand scheme of things, is that they are different molecular weights. And so they respond differently to different ambient conditions. And so what you end up happening is we've got oxygen isotopes, which are frequently used to reconstruct global temperature change. So we get oxygen isotopes have two different stable forms of oxygen isotope. There's 16 and there's 18. So they have different molecular weights. 18 is heavier. And it's really closely tied to the water cycle because water is H2O, right? So oxygen is right there in the name. So you get water incorporated into, you get oxygen incorporated into water. So we get water containing lighter oxygen isotopes is going to selectively evaporate more easily than the heavier oxygen isotope. So 16 will evaporate more easily than 18 because 18 is heavier. So then that rain cloud of evaporated water is now going to move over a landmass and it's going to rain out. It's going to selectively rain out the heavier oxygen isotopes because it's heavier. So 18 rains out a little bit more. And then when it finally passes over the high mountains and it snows out, then the snow that comes out is going to have really low relative levels of oxygen 18. So you get, if you look at the number of, if you look at the ratio of heavy to light oxygen isotopes, you can predict with relative accuracy what the temperature would have been, because if it's really cold, that oxygen 16 rich snow is never going to melt and come back down to the ocean. So you can look at the ratio of the two of them. So basically what we see is that if you have a really high relative oxygen 18 ratio, that means it's colder. And if you have a relatively low oxygen 18, that means it's hotter. And so with the colder one, that just means more of the 16 is still frozen on top of a mountain. And the reason that that's relevant is because we get the way that we reconstruct this global change is by looking at the ocean. So how do we actually measure these changes over time? So we've got these teeny tiny little microscopic microscopic shells, essentially. Or microscopic organisms that are living in the oceans. Those shells are going to incorporate a lot of the oxygen in the ocean water around them. And so when they live in the ocean, they're going to incorporate that oxygen, and then the oxygen will be a record of whatever kind of the relative oxygen values were at that time that that shell was formed. So then when they die, they lay flat on the ground at the bottom of the ocean along with a bunch of other stuff. And then over time, you'll get this nice continuous sequence of what's happening with temperature change over time. And so we can look at those changes over time by going out these big coring vessels and going out onto the ocean and sticking a drill down into the seabed and extracting these big oceanic cores. And then you can look at those cores and look at the individual oxygen isotopes within each layer, and you can look at this change over time, which is really amazing. So we've done this all over the world. There's like, hundreds and hundreds of drilling sites. And so we've been able to piece together a really good understanding of how the climate has shifted over time, which is very exciting if you're interested in fossils. So we can use these data to reconstruct these large scale records of temperature change over millions and millions of years. So this graph, you're going to see it a couple times. And I'm sorry I'm showing so many graphs, but so this graph is showing, you read it kind of right to left. So over on the right side where it says Paleocene, that's the oldest, and that's right after the dinosaurs go extinct. And then all the way over on the left is the recent. And so on our y-axis, on the left, we've got relative oxygen isotopes. So this is showing us our relative temperature. And then on the y-axis, or the x-axis on the bottom, we've got time. So what this is showing us is that right after the dinosaurs go extinct, we get this gradual increase in temperature in what's called the Paleocene. So the first 10 million years after dinosaurs go extinct, we have a gradual increase in temperature. This is global. And then immediately following that, we've got this epoch called the Eocene. So this is 56 to 33 million years old. And this is the really special time period for the Bighorn Basin, because we've got this Eocene record that begins with this massive, massive spike in global temperature. And so for the first 10 million years of the Eocene, you've got almost globally tropical conditions. And so you have tropically adapted mammals for that first kind of 10, 15 million years of the Eocene. And then you have gradual cooling over the rest of the Eocene into more seasonal environments. And so you can look at how animal communities are changing in response to those global environmental changes. And this spike in temperature at the very beginning of the Eocene is really, really interesting. So this is something called the Paleocene-Eocene thermal maximum. I'm just going to call it the PETM because that's what most people call it, and that's easier than Paleocene-Eocene thermal maximum. And this time period was really cool because in the blink of an eye, like 10,000 years, which is nothing in geological time, in only 10,000 years, we get this massive spike in temperature. So we get a global warming by like 10 degrees Fahrenheit, and then it stayed that way for about 150,000 years, which is also a really short time period in the grand scheme of things. So in a geological sense, it's a very short time period. So this sudden spike is the PETM. And we do have hot conditions that immediately follow it, but the PETM in how sudden it happened is a really important time period for kind of thinking about comparisons we can make with our own understanding of climate shift over time. So what does that temperature shift even look like? And I had, when I first started working on this, I had a really hard time conceptualizing what, an increase by 10 degrees would even mean. So during the PETM, we have tropical conditions in the Bighorn Basin, and we get a temperature shift that meant that we would have had about 78 degrees Fahrenheit would be the average annual temperature. For comparison, the average temperature in Meeteetse is 40 degrees. So just think about if you had lived in Meeteetse 56 million years ago, you would have been living in essentially, the Costa Rican rainforest kind of heat. So this is a really, really crazy environmental difference. And it should be noted that, it didn't look like modern day Wyoming immediately before the PETM. So we've got kind of these tropical deciduous forests right before the PETM. So you can kind of think of maybe North Florida or or central Florida, kind of that environment would have been similar to what we saw in the Bighorn Basin immediately before the PETM. And then at the PETM, we get this dry, deciduous tropical forest where you have really seasonal rainfall. So you can think of things like the central Mexican forests. So it still would have been really tropical and really hot, but it also would have been really dry and actually quite challenging for animals to live there sometimes. And so not only was there this temperature shift, but we also have this really dramatic environmental shift. And then with that, there comes a lot of interesting changes in the animal communities. And there are very few places in the world where you can see this transition happening. So there are not many places that show what's happening before and after the PETM. And so we get, you can look out on the landscape. If you know what you're looking for, you can look out on the landscape and see the marker beds for the PETM beginning and the PETM ending. If you've been driving up around Polecat Bench, you can see very easily this thick red band along the western edge that's marking quite distinctly that PETM transition. And this isn't just in these isolated places. You can see this transition in other places throughout the Bighorn Basin. So this is a map of University of Michigan fossil sites in the Bighorn Basin. And so this is showing different sites of different ages represented by different colors. And so what we're looking for here is if we see a combination of reds and greens, that's where we're going to find a PET, or that's where we might find a PETM transition. And you can see that there's a lot of that kind of transitional point within the Bighorn Basin. So we've got a lot of data to go on, essentially. And with all of this data comes a lot of responsibility. You have to kind of ground it in a lot of important information with respect to kind of context that you're finding it in. So from all that data, we can get a really, really good idea of how animal communities are responding to changes across the PETM. So this red line here is showing the PETM. So that global spike in temperature really, really sudden. And this is obviously a very heavy diagram, and we're going to go bit by bit to explore this graph a little bit. So first, all of the bars that are currently visible are different ways of measuring age and environmental conditions. And it's really, really important to have all of that information if you're hoping to kind of make the most of whatever fossil material you have. So this is actually one of the reasons why it's really not a good idea to pick up a fossil if you find it. Because leaving it in context allows people to then, it allows a paleontologist or a geologist to come in and take a look at the context of that fossil and be able to make sense of it before interpreting it, essentially. So once you actually have that context, which is really critical to establish, especially if you're talking about environmental shifts, then you can start to say things about how animals are responding to this event. So again, we've got this kind of spike in global temperature showing that PETM marker, and then these are just different rock layers. So we've got all that we need to interpret it here. And so the first thing that I want to point out about this graph is that we've got a number of animals that go extinct at this massive spike in temperature. So things like Champsosaurs, these are kind of crocodile kind of things that would have been living in the Bighorn Basin prior to this global spike in temperature. Things like Plesiadopus, which is this weird little squirrely primate relative. These are animals that would have been living in the Bighorn Basin that went essentially extinct at this event. And this is really important to keep in mind because the PETM is often used as a really wonderful model for what is happening with ongoing climate change. So if we have ongoing climate change, we're having this spike in global temperature as we speak, and a lot of people are interested in how the animals that are alive today are going to be either more or less threatened by that change in environmental conditions. But it is kind of important to keep in mind that the PETM happened over 150,000 years, whereas our current spike in temperature is at a completely different scale. So the PETM is a really useful a useful model to understand how these animals are going to respond to this, but it's not necessarily a perfect analogy. And it's certainly not an indication that the spike in temperature that we're seeing today is anything like any of the ones we've seen in the past. This one we're seeing today is very anthropogenic, very driven by humans. Okay, so keep working through this graph still. So, okay, so we've got some animals that survive across this event, which is really cool. And one thing that's really amazing about them is that they do some really weird things with their body size. So we've got things like these strange kind of hippo, rhino, cow kind of things called coryphodon. And these are actually really common in the Bighorn Basin. If you find a lunky piece of bone, it's probably coryphodon. We also have a lot of rodents, and we've got something called haplomylus, this quite small animal. And all of those things are going to survive across the PETM. And what's really interesting is you can actually look at a tooth, just a tooth, and oftentimes that's all that fossilizes, is just a single tooth. You can look at tooth and you can understand a little bit, the size of that animal. You can use it to predict how big it was, what its diet was. You can learn a lot from just a tooth. And one of the things that we've been able to kind of understand about this dramatic climate event is that animal body size changes quite dramatically across the PETM. So we actually have a sudden dwarfing of a lot of these animals at the PETM. So there are animals that live across that, and then right at that interval where it gets really hot, they just drop off in body size. And we don't really know why this happens. It's been proposed that maybe this has evolved as a way of more rapidly cooling your body when it gets really, really hot. But again, you got to think about the scale at which that can happen. If that's a way to survive, we can't really expect animals today to do the same thing, right? It's too fast. And we also have some animals that are appearing really suddenly at this event. So things like artiodactyls, so pigs, deer, at the time, these were all really, really small, kind of a cross between a very tiny deer and I'm struggling here, maybe like a large rodent, or all these animals are quite tiny at this time period. And a good example of that is horses and perissodactyls. Things like horses appear at this event as well. And also primates appear at this event. So primates is actually, what brought me into this world of paleontology in general, because I actually am within an anthropology department. And so I'm really interested in how tropically adapted primates were able to live in North America for as long as they did. And there's a really interesting kind of migratory pattern that we now understand based on how old some of the fossils we found on other continents are. And so we know that at the beginning of the Eocene, at this PETM, this Paleocene-Eocene thermal maximum, we get the rapid appearance of primates, horses and their relatives, and deer and their relatives. And we have a few fossil sites in Asia, and then a bunch in Europe, and then just a ton in North America. And so we've been able to, using that geological context to understand how they're all related to one another, we've been able to figure out that they first appear in Asia, and then they appear in Europe, and then they appear in North America. And so we know that primates are evolving in North America, or evolving in Asia, and then coming over to North America right at the beginning of the Eocene. So that kind of spiking global temperature created these tropical conditions that allowed these very tropically adapted animals to get from one place to another. And so this is just a really interesting time period when we see these modern orders, these modern groups of animals evolving and appearing in North America. But something that I think about a lot, and this is kind of leading me into my own research now, is what did they arrive to when they got here? And I want to talk pretty briefly about how the Bighorn Basin and the beautiful mountains that characterize it today came to be. So in the late Cretaceous, so the mountains that are there have not always been there. And it wasn't until the late Cretaceous, so right when the dinosaurs go extinct, right around when the dinosaurs are going extinct and mammals are first kind of getting going, and after that extinction event, we've got the bighorn, the northern bighorns, the priors, and the beartooths all begin to rise in the late Cretaceous and the Paleocene. And they kind of continue that a little bit into the Eocene, but basically between 90 and 60 million years, they're lifted, and then they're kind of done. And then we get between 58 and 56 million years, we get the southern Bighorn Mountains and the Owl Creek Mountains rising. And then in the early Eocene, we get, or the early to middle Eocene, so between 56 to 46 million years, we get extensive volcanic activity in the Absarokas. And that volcanic activity lasted for a while and created these big, beautiful mountains that characterize the view to the west. So these are kind of the events that shaped the Bighorn Basin, but it is important to note that they didn't all come at the same time. And so when primates got to North America, the Absarokas were just beginning to form. And so this is something that I've been focusing a lot on recently. So kind of what is shaping this Bighorn Basin landscape are those rapid mountain uplift events. So the environment that you see today is very, very different. And that's important for a couple reasons. The first, or kind of the primary reason, what I'm going to talk about today and what really drives my research is that animals kind of live in certain areas, or a lot of animals will live in certain areas. So this was this famous study that was done back in the 60s, where this man looked at how many animal species lived in each kind of region of North America. And what he noticed was that as you get to areas where there are more mountains, so in the Appalachians and in the Rockies, the Sierra Nevada, you get increased numbers of animals. So you have more species where you have mountains. And this is something that he first proposed and he thought about a lot. And we've only seen it kind of borne out by more and more studies. So animals are, tend to be more animals in mountain regions. And I mean that in terms of mammals, which is what I primarily study, but I also mean, not just animals, there's also more plants. There's just higher biodiversity in mountain regions. And it kind of makes sense if you look at this picture of it's probably Hawaii or something, but if you look at this picture, you can see that there's a really complicated environment. There's really interesting kind of forest structure and deep ravines where things might live. And so it makes sense that there's higher diversity a little bit. So this is this site in, or this is this mountain in Borneo called Mount Kinabalu. And at this site, if you walk up the mountain and you track how many species you find in different places, you'll find that plant diversity peaks around 1.5 kilometers. And mammal diversity peaks just under 2 kilometers. So you do have kind of peaks in diversity as you move up the mountain. And so that happens for a bunch of reasons. So one of those is that you can have animals that are going to be adapted to really high elevation environments, right? If you live at high elevations, it's tough to live up there. It can be colder. The wind conditions are different. The oxygen levels are different. You have to adapt to it a little bit. And then you're also going to have low elevation animals. And when you've got high elevation animals and low elevation animals, there's going to be some area where they overlap in the middle. And so you might get this kind of mid elevation region where you get higher diversity of those animals. There's also the idea that these regions serve as a speciation pump, which is a really silly name for what it is, which is that when you get increased topography, you get increased opportunity for speciation, and you get kind of increased likelihood of an animal evolving something new that's going to be successful in that environment. We also have this idea of refugia, which just means that if an animal is forced into a new region, it's more likely that they're going to be successful in that region if it's a region with more topographic complexity, just because there's more kind of ecological roles that animal might fill in that environment. So you tend to get higher species diversity in these regions of higher topography. And these patterns tend to be really, really strong in the tropics. And I bet you can see where I'm going with this. So we've got tropical conditions in the Bighorn Basin during the Eocene, and that complex topography probably plays a really important role in speciation and extinction, and how animals are able to change through time and how they're able to survive through time. And so what I spend a lot of my time doing is working in the mountains around, or working in the Absaroka Range just west of Meeteetse. And so I focus on the Absaroka province, or the Absaroka volcanoes, for the reason that they have been mapped out really well. And I'm not a geologist. I'm not expecting to go out there and be able to determine exactly which volcano erupted first, but there's a really nice series of studies that have been done that show that these volcanic eruptions kind of followed each other in this sequential way. So the more northern volcanoes that are kind of in Montana, those erupted first, and then we get a little bit further south, the Sunlight Volcanic group starts going and casts volcanic ash and sediment all over the place. And then we get the Thoroughfare Creek group. So right around Meeteetse, we've got, this big purple guy sticking out here. That's Carter Mountain. So we have this really amazing volcanic activity, and we've got a really good understanding of when that volcanic activity actually happened. And so you can say with some degree of certainty that there were mountains in the Eocene, and we can say that these were the animals that were living on these mountains if we can find the animals, if we can find the fossils on the mountains. And so I work in this region here. So this has kind of these two later eruptive events. And so we know, based on the timing of those volcanoes, that they were high elevation at the time that fossils were deposited in this region. And we also know, so we know that because of the volcanoes, and then we also know that because there's a series of more stabilized topes. I'm not going to get into this one, but more stabilized tope work has revealed that they were high elevation at the time that the animals that lived there, 48 million years ago, when they lived there, it was a high elevation site. So I kind of focus on these interesting fossil occurrences and think about what it means in terms of biology and the processes that we know drive modern biodiversity today. And in particular, those processes that I just talked about, where you have kind of higher diversity in regions of high topographic complexity. And so I look at, I have a few different sites just in the southern Absaroka range. And so we get things like unique species, so species that are not found anywhere else. So we've got a couple of those on Carter Mountain. We've got some of those down in the Owl Creek area. We also have really weird fossil occurrences. So there are a couple sites on top of Carter Mountain that have crocodiles, which is crazy because today crocodiles don't live higher than like 150 meters. But at the time that those animals lived there, Carter Mountain would have been about 3,000 meters. So it's a little bit of a difference there. And it kind of makes you think really critically about, what are the range of conditions that these animals actually can live in? And why are we seeing them in different places in the fossil record? What does it mean about their extinction pressure and their speciation likelihood and their survival rates? So we get weird things like crocodiles. We also get presumed ancestor-descendant pairs that are found together. So this is a little bit more, a little bit more confusing to explain, except that usually we assume that you get one layer of rock with an animal in it, and then in the next layer of rock, maybe you'll get its descendant. And then in the next one, you'll get maybe that one's descendant. But if you're getting both of them in the same site, then it seems like we might have questions about how that speciation is actually happening. And so there's some kind of interesting occurrences that I'm seeing at these high elevation regions. We also get really high diversity of primates. And this pleases me greatly because I'm studying primates, but it's also just really interesting because in modern ecosystems, primates are really, really susceptible to extinction pressures because of climate change. And so thinking about the role that these high elevation regions play in allowing these animals to survive a little bit longer is really important for understanding what's called environmental tolerance. And so this graph is showing the elevational ranges of different mammals in Ecuador. And so it's showing you that for any one of these species, they can live in a range of environments. And so what's important to think about here is some animals are more able to live in a range of environments, and some have a very, very narrow window of environmental conditions that they're able to live in. And so really what I'm trying to do when I am working up on these high elevation regions is trying to get a better idea of how we can understand that in the fossil record and how that can help us better interpret some of the data that we have generated from this already just ridiculously expansive and wonderful Bighorn Basin fossil record. So I'm trying to understand or trying to expand what we know about some of these animals that we already know about. It also, studying these regions also allows us to understand kind of what happens to these mountain adapted populations during climatic cooling. And so the most of the Eocene is characterized by this gradual cooling, but it starts from this place of like global tropical conditions. And so it's really important to understand kind of how those animal communities are changing. We might expect kind of downward migration of certain mountain adapted species, then coming in contact with these lower elevation populations. And so in order to understand kind of community dynamics or regional animal dynamics, you need to have a good idea of where you're actually finding different animals, even in the fossil record. And also over the past century, we've had a lot of kind of range expansion of some animals, like in the Sierra Nevada and the Great Basin. We've had animals moving upward in their elevation range, and it's directly associated with aridity at lower elevations. And so this seems like a way that animals are able to persist a little bit longer and not go extinct as quickly, but then they're kind of messing with the high elevation animals. And so there are very real conservation questions to be asked and answered using this fossil data, and kind of thinking about how animals in the past can bear on our understanding of what's going on with the future. And all of this is kind of coming, I hate to use the word biased, the biased fossil record, but the fossil record of the Bighorn Basin is tremendous. It is truly outstanding. And all the basins in Wyoming have this amazing record of fossil species, but there's very little work that's done in the mountains. And a lot of times that just has to do with you're less likely to get fossils in the mountains. And so whenever you find them, it's a big deal. And so this kind of biased fossil record where we're focusing exclusively on these lower elevation regions has probably influenced our understanding of environmental tolerance over time, because you can use fossil data to understand, predict extinction rates and speciation rates. But if we don't have these critical regions where animals are able to kind of break the mold of their environmental constraints, we're not going to have a good idea of how animals are actually responding to change over time. So yeah, that is all I've got for you guys today. I want to say thank you to Amy Phillips for organizing this and kind of keeping in contact with me through this very weird time. And kind of fieldwork has and always will be a team activity. So if you guys ever want to do fieldwork, please contact me, and I should have put my email address here. But I also want to thank the Churchill family, the Punoyer family, Phil Gingrich and Holly Smith, Larry Todd, and then the folks who have supported my research financially, as well as all of the field assistants who've ruined their knees and froze their butts off climbing Carter Mountain with me. So.
All right, so we've got a couple questions if you're game to answer them.
Yeah.
All right, so would the shift in primates from Asia to Europe to North America be due to sea rise and exposure of land bridges, or more the effect of the tropical environment allowing for primates living at higher latitudes and rafting to other continents?
What a terrific question. Probably a combination of things. So the continents were definitely in slightly different places than they are today. And so there would have been a little bit more in the way of land bridges that would have been periodically exposed in those higher latitude regions. And the reality is we don't have a really amazing fossil record of the Arctic Circle. And so hopefully one day we'll be able to say what those environments actually looked like. But we do know that there's like palm trees and tropically adapted animals up there. So there definitely was forest that was compatible with primates. Yeah.
Is there, so like with archaeology and melting ice patches and things like that, there's kind of like the massive rush to like gather what's there. Is there something similar in paleontology for that area?
That's a good question. To be honest, I don't really know. I I don't know many other people. I don't really know anybody else who works at high elevations and does paleontology. So it's really just me mad rushing for things. And actually, when the snow melts, that's great because there's more erosion that will expose new fossils. And so that's what we want. Getting to them before they fall off the mountain is the trick.
Yeah. So any ideas or theories why the PETM occurred?
There's a lot of competing literature, and a lot of it has to do with kind of release of methane gases for some reason. There was a lot of weird tectonic stuff that was going on, which could have released some deep sea methane reserves, which probably contributed to it, but we don't fully know, to be honest.
Can looking back at how animals have adapted to certain environmental conditions in the past help with conservation issues today?
Yeah, absolutely. I think that, you're never going to have a one-to-one relationship, and so you're never going to have something that you can perfectly apply. But I really think that studying animals that we know are susceptible today to extinction pressures and studying them in the fossil record to understand why they might be susceptible to certain shifts is directly applicable to modern conservation initiatives.
Is anyone doing work that you know of that's like directly involved with that?
So I don't know I know that there are some people who use terrestrial mammals. There's a lot of people who will look at extinction rates using things that have a really crazy fossil record, like all of those plankton that I was talking about. They'll look at kind of extinction rates in those and try to extrapolate extinction rates in other organisms. But I think that if we can develop a good enough fossil record, you should be able to apply the same methodology to terrestrial mammals.
And how difficult is it to find fossils in the mountains versus the basin? And so like looking at, Meeteetse versus what's in between Warland and then Ten Sleep.
Right. So those, the really dry, arid areas where you've got badlands exposed, it's obviously going to be much easier, or not obviously, but it's going to be much easier to find fossils in those regions just because you've got less vegetation. And so the problem with working in the mountains is that it really varies on a year-to-year basis as to how much, if there was a lot of rain that winter or a lot of snow that winter, sometimes, I've been up there and there's still snowpack, but there's other times there's just too much grass to see anything. So it really varies. It's less predictable whether or not you're going to find fossils in the mountains. And there's also other technologies that you can utilize to predict where you might find fossils. So people use satellite imagery to figure out where rock exposures are. But those are often by the time those are updated, they often get updated every year or two, but it's usually not at the time scale you need to be able to decide whether you're going to go look on that mountain that year.
Do you see any potential hybrid animals in the presumed ancestor descendant pairs? I can't talk.
Oh, probably. It's tough because when you're looking at fossils and all you have to go off is a tooth, then really you just have, on average, this species is this size, and on average, this species is this size. And I'm sure that there is some misidentification of species based on that. But that's really all we have to go on, unfortunately. Yeah, there probably are hybrid, and I don't know if it's technically hybrid or just a different species or what, but it would be very hard to tease apart using the minimal data that the fossil record provides.
So how do you go from a jawbone to this is such and such a species?
Many, many hours of staring at it and being frustrated first, and then usually reading for many, many hours and then staring at a lot of other fossils and trying to decide why it's not this one and why it might be this one and why it might not be this one, and ultimately coming up with something that, to the best of your knowledge is correct. And then you might talk to somebody else and they'll be like, oh no, I found one that looks just like that. Stuff.
And how, I don't know if anyone's looked into this, but how kind of are the rates, if there's like an individual difference versus a difference that is going to make a different species?
Oh God, I don't know. Yeah, to be honest, I really don't know. I'm sure there are people who look at it on like a developmental level.
Mm-hmm.
And I'm sure that's a good way of doing it. But the reality is there's always going to be a lot of variation within a species. And so we usually assume that the fossil record is a dramatic underrepresentation of the actual diversity of a region.
What is your favorite like tidbit of knowledge or whatever, something that you've learned about your sites up here or something involved?
Oh gosh. My favorite tidbit of knowledge. I have no idea. It all feels so cohesive. It's hard to pull out tidbits, I'm afraid.
What's your favorite bit about it then?
My favorite bit about it is working in somewhere so beautiful, and it's nice to work in a region where there has been paleontology going on for, over a century and still feel like I'm finding brand new things. And I know that everybody who works out there feels that way. But it's cool to be in a region where really nobody else is working. It's very empowering.
Awesome. Oh, and we have one more question. What is your favorite story from the field?
Ooh, what is my favorite story from the field? Okay. My first time climbing up Carter Mountain, I had no idea where I was going, and I had my dog with me, and he saw a marmot, and I had only recently got him, and so he was on a leash, and this was a terrible idea. This was like a terrible disaster story. He was on a leash, and he saw the marmot, and he starts running down the hill after the marmot, and he pulled me, and I fell like 8 feet off of a little cliff, and I landed on a rock and sliced open my leg really bad. And it was stitched up by Tom Churchill, actually, which is why he's thanked on this slide here. But yeah, it was terrible. I was, at 10,000 feet, and I had a giant gushing wound on my leg. But it was a wonderful day because it was the first day that I was able to it was the first day we found fossils. And so even though it ended terribly, it was like amazing day anyway.
That's hilarious. Awesome. Well, thank you so much for joining us. Make sure if you're watching this on Facebook or here on Zoom, that if you have any other questions, get those into us now. If you don't, when you leave the webinar, it's going to take you to a survey. That really helps me when I'm planning museum programming. So if you can fill that out with your thoughts, and that would be great. And I'm not seeing any other questions coming in. If we do, I will send those your way. Can you repeat how to get in contact with you one more time?
Oh, sure. You can contact me. My email address is ilundeen@utexas.edu. Yeah, and if you see me around Meeteetse, say hi.
Awesome. Thank you so much for joining us. And if we have any questions come in last minute, I will send those to you via email.
Great. Thank you.
Awesome. Thanks.